Welcome to Textbook Toonz. Whenever three infinite lines cross in a flat plane, they trap an enclosed two-dimensional region, the triangle. This creates three structural components: corner points called vertices, straight segments known as sides, and three interior angles. List the corner letters in any order: ABC or YZX. It describes the exact same trapped space. But watch what happens if all 3 points align perfectly on a single path. The enclosed region collapses flat. To form a functional shape, points must avoid sharing the exact same straight line. In geometry, this rule is known as avoiding collinear points. Let's try to build the most balanced triangle in the world, an equilateral triangle, where every single side measures exactly 4 centimeters. Draw a 4-centimeter base, then pivot a ruler to guess the angle of the second side. The final gap reads 4.6 centimeters. Too long. You adjust the angle lower, but now the third side reads 3.5 centimeters, far too short. Standard rulers are designed strictly for measuring existing straight paths. They cannot predict the exact future meeting point of two angled lines. To lock in the correct third vertex on the first try, we need a tool that tracks distance in all directions. This diagram illustrates the mathematical reality of a circle. It represents every possible point that shares an identical, fixed distance from a center. To physically track and lock in these fixed distances in all directions simultaneously, we use the compass. Let's use the algorithm known as side-side-side construction, starting with our foundational 4-centimeter base. Set the compass width to 4 centimeters. Anchor it on the left point, and sweep a wide arc. The third corner must set on this path. Next, without changing the width, move the compass to the right point and sweep a second identical arc. The point where these two arcs collide is our final vertex, point C. Because this single intersection point sets on both circular paths simultaneously, both new sides are exactly 4 centimeters long. The tool removes all the guesswork. This overlapping circle mechanic works for any valid combination of unequal side lengths. Take a scalene triangle with sides of 4, 5, and 6 centimeters. We start again with our 4-centimeter base. We use the compass to map a 5-centimeter distance from the left point and a 6-centimeter distance from the right point. Their specific collision point builds this lopsided shape instantly, without requiring any manual angle adjustments. The same logic applies to an isosceles triangle. Using two circles of the exact same size over a base inevitably creates a shape with two equal sides. Geometry functions as a strict algorithm. If you input the 3 side lengths, the invisible collision of the radii dictates the final shape. Every triangle reveals the hidden skeleton of colliding circles. This brings us to a final challenge from the Grand Mathematician's textbook to test your spatial logic. This diagram shows two identical overlapping circles. The center of circle A sits on the perimeter of circle B, and circle B passes directly through center A. Connect the two centers to their top intersection point. What specific type of triangle is formed? Look closely at the radii of both circles to deduce the hidden side lengths, and drop your answer in the comments. Using the compass allows you to move past trial and error, giving you the power to build complex geometric shapes with absolute, undeniable certainty.